Just when I thought that I understood potentials, I saw weird statements like this. Electric potential at some point P equals negative 300 volts. And my brain was like, hey, what does that negative sign even mean? What does it mean to have negative energy? Well, by the end of this video, we will have a much deeper understanding of what electric potentials are, and we'll be able to understand what negative potentials mean. So just to quickly recall, what does it mean to say that potential at some point is 11 joules per kilogram? It just means that if I were to keep a 1 kilogram object over here, then that would have 11 joules of potential energy. But I could keep 10 kilogram object over here and it would have 110 joules of potential energy. It's an indicator. Similarly, what does it mean to say that at a point, the potential is 5 volts? Well, 5 volts is just 5 joules per coulomb. And so that means that if I were to keep a coulomb of charge, let's say a rock which is positively charged for some reason, and let's say it's 1 coulomb, then it would have 5 joules of potential energy. But I could keep 100 coulomb of charge over here, and then it would have 500 joules of potential energy. It's an indicator of how much potential energy it would have per coulomb. And if you're not familiar with this concept or need a refresher, we've talked more about this in our previous videos on Introduction to Electric Potential. Feel free to go back and check that out. But let's dig a little deeper this time. Remember, what does it even mean to say that potential energy of a kilogram is 11 joules? What does that number represent? Do you remember what does potential energy even mean? Well, we've talked about that. What this really means is that if I were to let go of this rock, let's say imagine I was holding that rock, and let's say I let go of that rock, then we know that rock is going to fall down, and as it falls down, its kinetic energy would increase. And this means that by the time it reaches the ground, all of that 11 joules is now converted into kinetic energy. That's what it means to have stored energy. That much can be converted to kinetic. And so this means when that rock comes from here to here, it would have lost all that 11 joules of potential energy. So do you know what we are really saying over here when we say VA is equal to 11 joules per kilogram? What we are really saying, and this is important, is that, let me write this down, is that if I were to call this point some other name, say B, then what we're really saying over here is that potential at this point is 11 joules per kilogram more than potential at this point. So let me just write that down and it'll make more sense as we talk more about this. So what I'm really saying is that potential at A is 11 joules per kilogram more than potential at B. This is what I'm really saying. Let me tell you why this is important. Now imagine instead of a ground, there was a table here somewhere. Now when I let go of this rock, it goes and hits the table and stops over there. And this time, by the time it reaches the table, do you think it would have gained 11 joules? No, it would have gained much less. Maybe only, I don't know, maybe only 3 joules of energy. Now what I would do is I would define the point over here. I would call this point as, say, I don't know, maybe T. And now I would say, hey, potential at point A is only 3 joules per kilogram compared to the potential at point T, because this is now a more convenient point to define potential. Depending upon which reference point we use, the potential at any point can change. In fact, there is no such thing as an absolute value of potential energy. The potential energy that you mentioned is always compared to potential energy at some other point in space. And to make sense of this, let me give you an example of something that you may be familiar with in maths, and that is a number line. If I asked you, hey, what's the position of this point? And I don't give you anything else on the number line, can you answer this question? No. You can only find positions relative to some other point. For example, you could say, hey, let me call this point as B. And now, if each one represents 1 centimeter, and to the right, it's increasing. So we could now say, okay, 1, 2, 3, 4, 5. We can now say, hey, this point is 5 centimeters more than B. This is how we really represent in our number lines. And most often what we would say is this reference is often called the origin, and we call it 0. And as a result, now this would become 5 centimeter plus 0 would become 5. But what's important is I don't have to call that 0. Maybe I could call some other point as 0, and I could call this as, I don't know, maybe 10 centimeters. Then this automatically becomes 15 centimeters. So notice what the value, the actual position really depends upon what you call this position. All right, but what's important, what doesn't change is that this will always stay 5 centimeters more than point B. And similarly, somebody else could say, hey, you know what? No, I don't want to use this reference point. I want to use this reference point, and we can call this as T. Now, with respect to this reference point, what is the value of this position? It's now just 1 centimeter more, 1 centimeter more compared to T. And so now if somebody likes to call this as my 0, and then this would be 1 centimeter, and so on and so forth. The same idea over here. Potentials are always with respect to some other point. And the exact same thing happens in electric potential as well, exactly the same thing. And that's why I love gravity, okay? So when I say potential at some point A is 5 volts or 5 joules per coulomb, what I'm really saying is that, hey, it's 5 volt more compared to potential at some other point, some other reference point. In this case, I may have chosen this as my reference point. So long story short, potential or potential energy is always represented with respect to some other point. If I call the potential here as 0, then the value of potential here is 11. If I call potential here as 0, the value of the potential over here would be 3 in this example. And for gravity, we most likely always like to choose the lowest point in our experiment as 0 or as our reference point. But what about when it comes to charges? What's our convenient reference point over here? Well, the most convenient point we like to choose is infinity. So in any scenario, if the reference point is not mentioned and someone says, hey, potential at a point, let me just write that. Potential at some point P is 30 volt. What does it mean if I don't mention in reference? It just means that it is 30 joules per coulomb. And that means that the coulomb over here would have 30 joules more potential energy than it would have at infinity. All right, so we always choose infinity as our reference point. So most of the time we like to choose this to be infinity, but it doesn't have to be, it's just a convenience. And so let me now show you a standard way of writing this. We often write this as potential at point A with respect to point B. That's how we like to write this. So this is my reference point, and we can call this as 5 volt directly. So this is the same thing as writing it this way. And you can also call this, so this would be just BA minus VB. So you can also write it this way. This also means the same thing. Potential at A, how much more it is compared to my reference point with respect to point B. And so this means whenever you're talking about potentials, you're always talking about the difference between the values of potentials between 2 points. And that's why we can also call this potential difference. So whether you call it potential at a point or potential difference between 2 points, it's really, really the same thing. And so now we can update our definition of potential. We could now say, hey, what does it mean to, what is the definition of potential at point P with respect to some reference point Q? We can now say, hey, it is basically potential energy that a charge would have at point P compared to at point Q per coulomb, per charge, okay? And this would be potential energy at point P minus the potential energy at point Q. You're basically calculating how much more potential energy it has compared to point Q divided by the charge Q. And for charges, most often this second point is taken to be infinity. So this second point is most often infinity. So I think we now have everything to answer our earlier question. What would it mean? So let me just, okay, there's no space over here. Let me go down. What would it mean if someone said, hey, potential at some random point P, electric potential was minus 300 volt? What is the meaning of this statement? Can you pause and try and explain this to someone now? All right, I would first say it is negative 300 volt is joules per coulomb. And what this now means is that potential at a point, if I kept a coulomb of charge at this point, it would have 300 joules of energy less compared to how much it would have at infinity, because our reference point is infinity. So now positives and negatives make a lot of sense because we are always comparing. If it's a positive potential, it's saying more potential energy compared to how much there will be at infinity. If it's a negative potential, we are saying, hey, less potential energy compared to at infinity. Just like in our number line, some positions can have negative values, meaning less value than our reference point, and some positions can have more values compared to our reference point. And finally, you can be even more curious and ask, hey, but how do we calculate the potential energy values in the first place? It's got something to do with work, and we'll explore all of that fun stuff in the future video.